Welcome back. We are looking at Chapter 2, Section 2, and we are going to look deeper into isotopes and perform calculations that relate the atomic weight of an element and the isotopic abundances and masses. So first of all, and this is not something that we are going to do in this Chem 120 class, but just to know that the masses of isotopes and their abundances are determined experimentally by mass spectrometry. So we do not actually, we will not be performing the experiments with a mass spectrometer, but that is how these are determined. So a mass spectrum is going to be a plot of the relative abundance of the charged particles versus the ratio of mass charge. So we can see the abundances over here on the y-axis, the mass charge. So we can see here that our neon gas that we are inspecting is going to go into the mass spectrometer, and it's going to vaporize first, ionize, accelerate here through these plates, and then the heavy ions are deflected not as much. So we can see the heavier, like the neon 22, that's the heaviest mass. And we can see the neon 22 here that's being shown in the plot. We've got neon 20, which is the greater of the three abundances. And then we have neon 21. So we've got three different isotopes being shown here. And again, it's just the mass spectrometer is giving us information on the mass and abundance of different isotopes. For example, we can look at a sample of boron and see that we have boron 11 and boron 10, and we have a greater abundance of boron 11. Same here with chlorine 35 and chlorine 37. We have a greater abundance of chlorine 35. So hydrogen has three main isotopes, and hydrogen is kind of special because we can actually call hydrogen 1, hydrogen 2, and hydrogen 3 specific names. Now, this is not, we don't have to, and other isotopes we won't be doing this, but hydrogen 1, if you've ever heard of protium, again, this is telling us that its mass is 1. Well, we know that hydrogen has 1 proton, so if its mass is 1, it must have 0 neutrons. So this specific isotope of hydrogen is called protium. Hydrogen 2, again, has 1 proton, so it must have 1 neutron, and this is called deuterium. Hydrogen 3, again, 1 proton, has 2 neutrons, and it's called tritium. So, again, sometimes it has a specific name, but we could also just call this hydrogen 1, hydrogen 2, hydrogen 3. How many protons and neutrons does an atom of lead with the mass of 206 have? Well, let's look at lead, Pb, on the periodic table, which is atomic number 82. So it has 82 protons. And to find out how many neutrons, we're going to do 206 minus 82. Is that 124 neutrons? So this is lead 206, just like this is hydrogen 2, hydrogen 1, hydrogen 3, and so on. Okay, let's look at this guy. We have carbon 12, carbon 13, and carbon 14. If all three exist naturally, then why is the atomic mass for carbon, if we looked on the periodic table, 12.011 and not 13? Because if we looked at this and we said, okay, I've got carbon 12, carbon 13, carbon 14. Let's find the average. 12, if we did a normal average like what we're used to, 12 plus 13 plus 14 and divide it by 3, we would get 13. Because that's right in between 12, 14, the average would be 13, right? Well, but that's a little bit different when I have different percent abundance. For example, carbon 12, I have 98.93% of my sample is carbon-12. 1.07% of my sample is carbon-13. And it says here that just trace, so not even enough to really count. So to find the average, we actually have to do a little bit of a different practice here. Let's fill in this chart. Atomic number we know of carbon is 6, 6, 6. The mass number here, we're told it's 12. This one's 13. This one's 14. We know atomic number and protons are the same, 6, 6, 6. We know electrons are all 6, 6, 6 because it's neutral. Now neutrons, here I've got 6, because 6 plus 6 is 12. 7, 6 plus 7 is 13. 6 plus 8 is 14. So here's what we do when we want to go about finding the average atomic mass. I take the mass number that it tells me here, carbon-12, times. Now this percent abundance, because 98.93% of it has a mass of 12. So I need to make that a decimal. So 0.9893. Then I need to take my next isotope, that mass, which is 13, and times that by this percentage that it's found. So I need to move that decimal back 2 spots, so it'd be 0.0107. Let's pause for a second and figure out what those two answers are. Okay, I got each of those separate answers, and then finally the last step, we add them together. And that gives me 12.0107, which rounds to 12.011. And then if I take another minute to look at this, my largest percentage, almost 99% of my sample weighs 12. Notice that my average is closest to 12, but yet a little bit bigger than 12 because 1% of my sample is 13. So it's going to be in between 12 and 13, but definitely much closer to 12. Okay, here's a little practice. Protons, neutrons in each of the following isotopes. Why don't you pause the video here, make sure that you can figure this out. Now this is a teeny bit sloppy. Let's see if I can do some color coordinating here. So both of these are chlorine. So they both have 17 protons. This isotope has 20 neutrons and this isotope has 18 neutrons. Both of these are tin. So they both have 50 protons. This first isotope has 70 neutrons and the second one has 72 neutrons. Uranium, here I got all my uranium right here. They both have 92 protons. The first isotope has 146 neutrons and the second one has 148. Mercury, they both have 80 protons. This one has 122 neutrons. That one has 124 neutrons. And similar to what I did in that first one with hydrogen, all of these elements, plus so many more, have isotopes with different abundances. So let's look at boron. 19.91% of this sample of boron has an isotopic mass of 10.0129, which you can see is rounded to 10. This one is 11.0093. 80% of the sample weighs 11. So when I find the average of this, it's going to be somewhere between 10 and 11, and it would be closer to the one that's larger percentage, so closer to 11, but in between 10 and 11. Let's look at neon here. Neon, 90% of this sample of neon has a mass of almost 20. And then the other 10% is about 21 and about 22. So it's going to be closer to 20, but a little bit more than 20 because not lower than 20, right? Because the other 10% is greater than 20, 21, and 22. Same with magnesium. We can see that there's 3 prominent isotopes. 79%, 10%, and 11%, having masses of almost 24, almost 25, almost 26. So let's do a sample problem here. We have naturally occurring chlorine. 75.53% of chlorine has a mass of, we rounded to 35, but its actual mass is 34.96885. So I'm going to write this down before we get too far. I'm going to say that mass, 34.96885 times that percentage is in a decimal, 0.7553. Okay, and 24.47%, so I'm going to make that a decimal, has a mass of 36.96590. Calculate the average atomic mass of chlorine. Also notice here that these two percentages, where did it go? These two percentages equal up to 100%. So this chlorine just has two main isotopes that we're going to be inspecting. So let's plug and check on our calculator, see what you can get for both of those, and then we're going to add up those two numbers. And we're not rounding to the very end. All right, let's see if this answer makes sense. So when I did this 34.96 times the 0.7553, I got 26.41197. And then I did the second isotope times its percentage, and then I added the two together, and I went to as many decimal places as I was given in my problem, which was 1, 2, 3, 4, 5 decimal places. And let's see if this average makes sense. So 3/4 of my sample had a mass of about 35. The other was 37. So when I find this weighted average, it's going to be between 35 and 37. And so therefore that makes sense, 35. Now what's it going to be closer to? 3/4 of it was 35. 1/4 of it was 37. So it'll be closer to 35, but greater than 35, right? So 35.457 makes sense. Here's an expression, so showing us what we're doing. To find the average mass of the chlorine, we take its mass of whatever atom it tells us times the abundance. So this is part 1. And then we add the mass of the second atom and then times that by its abundance. And then we got 35.45, which is what our periodic table tells us. Let's try another example. Gallium has two isotopes. One has a 60.11% abundance, the other has an almost 40% abundance. See if you can set this up. So pause the video here, give this a practice, and I will have the answer in just a second. Check to see if you got the same answer I did. Again, I went to 3 decimal places just because my question that I started with went to 3 decimal places. And I got an average atomic mass, or AMU, average atomic mass units, of 70.264. Again, that makes sense because 60% of my sample had a mass of about 69. Other had a mass of 71. So to have a mass of 70 makes sense. Here's another practice. It's the second most abundant element in the Earth's crust. Calculate the average atomic mass for silicon. See if you can do this one. I'll pause the video. All right. Be careful when you are converting these percents into decimals. A lot of people just want to make this 0.47, but that would be 47%, not 4%. So be careful. Make sure that you have that 0 in front. And did you get the same answer I did? 28.086 AMU for silicon? Hopefully you did. All right, let's do another one here for copper. We have copper 63 and copper 65. Why don't you pause the video and see if you get the same answer I do. And I got 63.548 AMU for my average. Let's do a couple of practice problems. Why don't you pause the video here and see what statement describes the composition of an isotope of iron 58. Pause the video here. Did you get 32 neutrons, 26 protons, 26 electrons? How about about this one? What is likely the most abundant stable isotope of gallium? Look at gallium on the periodic table. Hopefully you got gallium-69 because its mass on the periodic table is 69.723 is its average. So the greatest percentage probably is 69 as opposed to 71. How about this one? Take a second. Pause the video. Hopefully you got 80.92. Here's another practice. And let's check your answer. Did you get 0.23% and 9.29%? Great. Let's move on to section 2.3.